What would you see if you fell into a black hole? Not metaphorically, literally. What would your eyes perceive? What would happen to your sense of time, your body, and your view of the universe? Would the stars swirl into impossible shapes? Would time stretch into infinity? Would you see the end of the universe, or your own past? These are not questions confined to science fiction. They are real, physical questions grounded in general relativity, quantum theory, and the frontier of modern physics. Black holes are not just cosmic vacuum cleaners or death traps. They are laboratories where the most extreme laws of nature are on display. To understand them is to confront the very edge of space, time, and reality itself. Let's begin. In the vastness of the universe, black holes occupy a strange place in our imagination. They are feared, misunderstood, and often dramatized as monstrous vacuums consuming everything in their path. Yet at their core, black holes are not fiction. They are real, measurable phenomena predicted by one of the most elegant and successful theories in physics, Albert Einstein's general theory of relativity. But if black holes are real, and we now know they are, what happens if someone falls in? More importantly, what would they see? This question might sound like a thought experiment. In many ways, it is. But it is also a serious scientific inquiry, one that forces us to bring together what we know from general relativity, quantum mechanics, astrophysics, and even philosophy. Because black holes push the limits of what nature allows, any attempt to describe what it feels like to fall into one brings us directly to the edge of our understanding of space and time. So why focus on falling into a black hole? Why not just observe them from a safe distance? The answer lies in what black holes reveal when approached closely. From afar, we can measure their mass, estimate their spin, and detect the X-rays they emit as they feed on nearby matter. But from within, from the perspective of something actually falling in, we encounter questions that challenge the foundations of physics itself. Questions about time, causality, information, and even the shape of reality. To see why this matters, let's briefly go back more than a century. In the early 1900s, physicists were wrestling with how to describe gravity in a way that went beyond Isaac Newton's laws. Newton had described gravity as a force between masses, instantaneous and universal, but it had no explanation for how gravity worked or how it interacted with light, time, or space itself. Albert Einstein changed that. In 1915, Einstein presented his general theory of relativity to the Prussian Academy of Sciences. It proposed that gravity is not a force in the traditional sense, but a curvature of space-time itself. In simple terms, matter tells space how to curve, and curved space tells matter how to move. Just weeks after Einstein completed his equations, a German physicist named Karl Schwarzschild found a solution to them. This solution described a point in space where gravity becomes so intense that nothing, not even light, can escape. Schwarzschild's mathematics defined a spherical boundary, later called the event horizon. At the time, it was just a mathematical curiosity. Even Einstein himself found the idea of such objects too extreme to be real. He believed nature would prevent such singularities from forming, but that view would not last. By the 1930s, the idea of black holes began to take shape through the work of theorists like Subrahmanyan Chandrasekhar, who calculated that stars above a certain mass could not support themselves against gravitational collapse. In 1939, J. Robert Oppenheimer and Hartland Snyder published a paper describing how a sufficiently massive star, after exhausting its nuclear fuel, could collapse under its own gravity into a singularity, a point of infinite density. This theoretical object would be surrounded by a boundary from which nothing could return. The black hole, as it would later be called, had been born in mathematics. Still, it took decades before black holes moved from theory to observation. In the 1960s and 1970s, the discovery of quasars, extremely bright objects powered by supermassive black holes at the centers of distant galaxies, provided indirect evidence that something like black holes really existed. In the decades that followed, scientists began identifying black hole candidates in X-ray binaries, where one visible star orbited an unseen companion. By the early 21st century, astronomers had built powerful tools like the Chandra X-ray X-ray Observatory, the Very Large Telescope in Chile, and radio telescope networks capable of tracking the dynamics of stars near the center of our Milky Way. These efforts culminated in two key achievements: the identification of Sagittarius A star, a supermassive black hole at the heart of our galaxy, and the landmark image of a black hole's shadow by the Event Horizon Telescope in 2019. These discoveries confirmed beyond doubt that black holes are real objects, not merely solutions to equations. They have mass, they bend light, they consume matter, and they shape galaxies. But they also defy our intuitions. The closer we get to the event horizon, the stranger the laws of physics appear. Time slows, light bends, space itself stretches in ways that challenge even the best trained minds. And yet, all of this describes only the view from outside. What happens beyond the event horizon remains one of the great unsolved mysteries of modern physics. Here, we encounter a key distinction in general relativity, the difference between what an outside observer sees and what the person falling in actually experiences. From the outside, an object falling toward a black hole appears to slow down, freeze, and fade away as it approaches the event horizon. But from the falling object's point of view, it continues onward, unaware of any boundary. It crosses the event horizon in finite time, and then continues deeper into space-time where the known laws of physics begin to unravel. To fully understand this journey, we must imagine falling in ourselves. This is not a trivial exercise. It requires rigorous thought, precise mathematics, and the courage to ask questions that current theories cannot fully answer. But it is also one of the best ways to test our understanding of gravity, time, and the structure of the universe. Scientists use the concept of an infalling observer to explore ideas ranging from gravitational time dilation to the behavior of light near massive objects, and even the fate of information swallowed by black holes. These are not idle musings. They influence the way we think about everything from cosmology to quantum computing. In this documentary, we will follow such a journey from the outer edges of a black hole's gravitational influence through the event horizon and ultimately into the unknown regions near the singularity. Along the way, we will draw from general relativity, quantum theory, observational astronomy, and the insights of many of the greatest scientific minds of the past century. To understand what someone would actually experience when falling into a black hole, we first need to grasp what gravity really is, not just as a force that pulls objects down, but as a fundamental feature of the fabric of the universe. This shift in understanding began more than a century ago, and it forever changed the way scientists describe motion, space, and time. Before the early 20th century, gravity was best described by Isaac Newton's laws. In Newton's view, gravity was an invisible force acting between masses. It explained everything from falling apples to planetary orbits. It was astonishingly accurate and incredibly useful, but it had limitations. It could not explain how gravity affected light, nor how it might interact with time. It also assumed that time ticked the same everywhere, regardless of your location or velocity. For over 2 centuries, these limitations remained theoretical concerns until the early 1900s, when new discoveries forced a re-examination of space and time itself. This re-examination culminated in Albert Einstein's general theory of relativity, published in the year 1915. Einstein proposed something revolutionary. Gravity is not a force in the traditional sense at all. Instead, massive objects like stars and planets bend the very fabric of space-time around them, and other objects move along these curves. In this view, Earth does not orbit the Sun because the Sun pulls on it across empty space. Earth orbits the Sun because it is following a curved path in space-time, shaped by the Sun's mass. To picture this, imagine placing a heavy ball in the center of a trampoline. The surface dips, and a smaller ball placed nearby will roll toward the heavier one, not because of a mysterious force, but because the fabric is curved. This analogy is imperfect, but it helps us begin to see what Einstein meant. Matter tells space-time how to curve, and curved space-time tells matter how to move. This idea was not just a philosophical shift, it made testable predictions. One of the most important early tests came in the year 1919. During a total solar eclipse, British astronomer Arthur Eddington led an expedition to measure the positions of stars appearing near the edge of the Sun. According to Einstein's theory, the sun's mass would slightly bend the path of starlight passing nearby, making stars appear displaced from their normal positions in the sky. Eddington's team confirmed this prediction. The effect was small but measurable. It showed that light, which had always been assumed to travel in straight lines, could be bent by gravity, not by pulling on it, but by curving the space through which it traveled. This was a major turning point. It meant that space and time were not fixed backgrounds, but dynamic entities that could be warped by mass and energy. It also meant that the geometry of space was inseparable from the flow of time. Einstein's equations of general relativity describe this warping using mathematical constructs called metrics, which encode the shape of spacetime around massive objects. In the case of a non-rotating, spherically symmetric mass, the solution is known as the Schwarzschild metric, named after Karl Schwarzschild, who derived it shortly after Einstein published his theory. The Schwarzschild solution describes how spacetime is curved around a simple object like a star or a black hole. Importantly, this solution showed that if the mass of an object is compressed below a certain radius, known today as the Schwarzschild radius, it creates a region where the curvature becomes so extreme that all paths, even those taken by light, lead inward. This region defines a black hole. But let us step back for a moment. What does it actually mean for spacetime to be curved? In everyday life, we think of space as flat. A ruler measures the same length no matter where you put it. A clock ticks the same whether you are standing in your kitchen or your garden. But these assumptions are only approximately true in regions of weak gravity. In strong gravitational fields like those near a black hole, space can stretch and compress. Time can run at different rates. This phenomenon is known as gravitational time dilation. It means that clocks closer to a massive object tick more slowly compared to clocks farther away. This has been confirmed experimentally many times. For instance, atomic clocks flown on airplanes tick at a slightly different rate than identical clocks on the ground. Even the global positioning system must correct for time dilation to maintain accuracy. Without these corrections, GPS location errors would grow by several kilometers each day. The deeper you go into a gravitational field, the stronger this time dilation becomes. Near a black hole, the effect becomes extreme. To a distant observer, an object falling into a black hole appears to slow down as it approaches the event horizon. Its motion becomes increasingly sluggish, its signals red-shifted, and eventually it seems to freeze in place, fading from view. But this is only from the outside. The falling object itself does not experience any of this delay. From its own perspective, it crosses the event horizon in a finite amount of time. This discrepancy between what the outside sees and what the falling observer experiences is one of the strangest consequences of curved spacetime. It is not an illusion or an error, it is a real difference, rooted in the way spacetime operates under Einstein's equations. As we descend further into the black hole, this curvature grows stronger. The rules that guide motion and measurement become more and more warped. Straight lines no longer exist in the usual sense. Even the idea of down loses meaning, because all directions lead inward. Light, which always travels along the shortest path between 2 points, finds its path constantly bent, its journey curved by the shape of the surrounding spacetime. In everyday life, we rely on the constancy of geometry. Parallel lines never meet. Angles in a triangle add up to 180 degrees. But in curved space, these rules no longer apply. Triangles can have more or fewer than 180 degrees. Parallel lines can converge or diverge. Distances change depending on how you move through the field. And because time is part of spacetime, it too becomes subject to distortion. This is not just theory, it has practical consequences. Astronauts aboard the International Space Station experience time slightly differently than people on Earth due to both their velocity and the reduced gravity in orbit. The difference is tiny, but measurable with precise instruments. General relativity teaches us that the universe is not a static stage, but an active participant in the play. Mass and energy curve spacetime, and this curvature governs the motion of planets, the path of light, and the ticking of clocks. Black holes are the most extreme examples of this relationship. They represent the most intense curvatures allowed by the known laws of physics. Understanding how gravity bends the rules of space and time is not just a curiosity, it is essential to understanding what someone would see if they fell into a black hole. because every visual cue, every movement, every moment of time is shaped by this curvature. The farther we fall, the stronger the effects become, until they overwhelm our ability to describe them using familiar concepts. As we've seen, gravity is not just a force, but a curvature of space-time, a warping caused by mass and energy. And nowhere is this warping more extreme than in a black hole. But before we can imagine falling into one, we first need to understand where black holes come from, what creates them, what conditions allow them to form, and how did scientists come to believe that such bizarre objects could really exist in nature. The story begins with stars, specifically with the life and death of the most massive stars in the universe. Stars are powered by nuclear fusion. In their cores, lighter elements like hydrogen are fused into heavier elements like helium. This process releases an immense amount of energy, which pushes outward and counteracts the inward pull of gravity. For most of a star's life, a delicate balance is maintained between this outward pressure from fusion and the gravitational pressure trying to collapse the star inward. But this balance cannot last forever. Eventually, the star exhausts its nuclear fuel. When that happens, the outward pressure weakens. Gravity, unopposed, begins to win. The core starts to collapse. What happens next depends on the mass of the star. If the star is relatively small, roughly up to 1.5 times the mass of our Sun, it might end its life as a white dwarf, a dense but stable object supported by electron degeneracy pressure. If it is more massive, it might collapse further into a neutron star, where matter is compressed into a soup of neutrons. But if the star is massive enough, beyond a certain threshold, the collapse cannot be halted. Not even the pressure from neutrons can stop it. There is no known force in the universe strong enough to resist the crushing pull of gravity. The result is catastrophic. The star implodes, collapsing inward toward a single point. The matter is compressed into an infinitely small, infinitely dense region, a singularity. The black hole is born. The precise mass limit that determines this fate was first calculated by a young Indian physicist named Subrahmanyan Chandrasekhar. In the early 1930s, Chandrasekhar was only in his 20s when he showed that white dwarfs cannot exist above a certain mass, about 1.4 times the mass of the Sun. This limit, now known as the Chandrasekhar limit, was not welcomed warmly at first. Arthur Eddington, a prominent British astronomer, famously disagreed with Chandrasekhar's conclusions, arguing that nature would somehow avoid such a collapse. But time and further research proved Chandrasekhar correct. A few years later, in the year 1939, another major theoretical breakthrough occurred. J. Robert Oppenheimer, working with his student Hartland Snyder, published a paper titled On Continued Gravitational Contraction. In it, they described a model of a collapsing star that, if massive enough, would continue shrinking until it disappeared behind a boundary, a surface we now call the event horizon. Their model showed that, for a distant observer, the surface of the collapsing star would appear to freeze and fade as it approached this boundary, due to the extreme time dilation near the forming black hole. But for the matter itself, the collapse would continue inward beyond the horizon, ending in a singularity. This was one of the first theoretical models to describe what we now understand as a black hole. Oppenheimer and Snyder's work was groundbreaking, but it was largely ignored at the time. The Second World War soon drew attention away from such theoretical concerns, and black holes remained a fringe topic for decades. It was not until the 1960s that black holes returned to the forefront of physics. This resurgence was driven in part by advances in astrophysics and in part by better observational tools. In the year 1967, physicist John Wheeler coined the term black hole, replacing earlier, less intuitive phrases like frozen star or gravitationally completely collapsed object. The new term captured the imagination and stuck. Around the same time, astronomers were observing unusual celestial objects. They discovered quasars, extremely bright, distant sources of light emitting more energy than entire galaxies. The only known explanation for such power was matter falling into supermassive black holes, millions or billions of times more massive than the Sun, at the centers of galaxies. X-ray astronomy also revealed binary systems where an ordinary star was orbiting an invisible companion. These systems, known as X-ray binaries, often emitted intense bursts of X-rays, believed to result from matter being pulled from the star and accelerated toward a compact, unseen object. In many cases, the inferred mass of the invisible companion exceeded the theoretical limits for neutron stars. The only remaining explanation, a stellar mass black hole. One of the most famous of these systems is Cygnus X1, identified in the early 1970s. It became one of the first strong black hole candidates and helped to establish black holes as real astrophysical entities. Meanwhile, theorists continued to explore the implications of black holes in general relativity. Mathematician Roger Penrose developed rigorous theorems showing that under general conditions, singularities were not mathematical artifacts, but real physical features of space-time. His work, along with that of Stephen Hawking, established that singularities are inevitable in gravitational collapse, provided certain energy conditions are met. The formation of a black hole, then, is not a speculative or exotic event. It is the natural end of certain stars, a consequence of physics itself. When gravity wins, the result is not just a dead star, but a new kind of object altogether, and black holes do not only form from dying stars. In the early universe, regions of extreme density could have created primordial black holes, tiny but incredibly dense objects that might still roam the cosmos. At galactic centers, supermassive black holes seem to have formed early and grown over billions of years, though the precise mechanisms of their origin remain an open question. What unites all black holes, regardless of their size, is the same basic structure, a region of space where gravity is so strong that nothing, not even light, can escape. The boundary of this region is the event horizon. Beyond it lies the singularity, and between them is a one-way passage toward an unknowable fate. In modern astronomy, we detect black holes not by seeing them directly, but by observing their effects. We see stars whipping around invisible centers. We measure X-ray emissions from matter heating up as it falls inward, and in the case of the Event Horizon Telescope, we observe the shadow cast by the black hole's gravitational influence on surrounding light. In 2019, the Event Horizon Telescope released the first-ever image of a black hole's shadow, located in the galaxy Messier 87. It was a historic moment, combining data from observatories across the globe to form a composite image of the dark center surrounded by glowing plasma. The image confirmed predictions made decades earlier and offered the most direct evidence yet of the existence of event horizons. Today, black holes are no longer speculative objects. They are observable, measurable, and central to our understanding of galaxies, high-energy astrophysics, and the life cycles of stars. But even though we now know how black holes form and where to find them, we still do not fully understand what lies beyond the event horizon. The extreme conditions inside a black hole test the limits of general relativity and demand a quantum theory of gravity, a theory we do not yet possess. To understand what it means to fall into a black hole, we must now confront the defining feature that separates the inside from the outside, the event horizon. This boundary is not a surface in the ordinary sense. It has no physical substance you could touch or see. But its consequences are absolute. It is the point beyond which nothing, not even light, can return. Once crossed, there is no turning back. The event horizon is often misunderstood. In popular imagination, it is portrayed as a sort of violent boundary, like hitting a wall or plunging into a whirlpool. But in reality, for someone falling in, the event horizon does not feel special at all. There are no visible markers, no sudden jolt, no change in the local environment. The laws of physics remain smooth and continuous as you pass through. And yet, from a global perspective, something profound has occurred. You have left the visible universe behind. The idea of an event horizon emerged from Carl Schwarzschild's solution to Einstein's equations, published in the year 1916. His mathematical solution described the space-time geometry around a spherical, non-rotating mass. Embedded in the equations was a critical radius, the Schwarzschild radius, at which the escape velocity equals the speed of light. Any object compressed within this radius would form a black hole, and the boundary at that radius would be the event horizon. This critical surface is not like the surface of a planet or star. You cannot stand on it or bounce off it. It is a one-way membrane. Anything can go in, but nothing can come out. Once an object crosses this invisible line, all of its future paths point inward toward the singularity. Even a beam of light, which always travels at the universal speed limit, cannot escape. In fact, to remain stationary at the event horizon would require moving at the speed of light in the opposite direction, an impossible feat for anything with mass. The term event horizon captures the essential feature of this boundary. It is a horizon for events. For an outside observer, no information or signal can emerge from within. Whatever happens beyond the horizon is hidden from the rest of the universe. It lies outside the causal structure of the observable cosmos. This creates a remarkable consequence. Imagine a spaceship falling toward a black hole. From the perspective of someone watching from a safe distance, the spaceship appears to slow down as it approaches the event horizon. Its clocks tick more slowly. Its signals are stretched into longer and longer wavelengths. Eventually, the ship seems to freeze just above the horizon, its light becoming dimmer and redder until it fades from view. The process appears to take forever, but for the crew aboard the spaceship, there is no such delay. Their own clocks tick normally. They do not freeze in place. They simply continue falling, unaware of the external perception. From their point of view, they cross the horizon in a finite amount of time and continue their descent toward the singularity. The difference between these two perspectives lies at the heart of general relativity and reveals the deep connection between gravity, time, and observation. This raises a natural question. If you cannot see the event horizon and cannot feel it, what makes it real? The answer lies in its effect on light cones. In relativity, a light cone represents all possible directions that light, or any influence, can travel from a given event. Outside a black hole, your light cone is open. You can send signals in any direction, including outward. But as you approach the event horizon, the light cone tips inward. At the horizon itself, it points exactly sideways. And beyond it, all paths, even those taken by light, point inward toward the center. You are no longer free to choose your direction. The future leads inevitably toward the singularity. Mathematically, this is expressed in the structure of space-time itself. In Schwarzschild coordinates, the metric becomes singular at the event horizon. But this is not a physical singularity, it is a coordinate artifact. Just as lines of longitude converge at the poles of Earth, certain coordinate systems can produce misleading infinities. By changing to a different set of coordinates, such as Kruskal-Szekeres coordinates, the spacetime remains smooth across the horizon. This shows that the event horizon is not a place where physics breaks down. It is a boundary defined by the global structure of spacetime, not by any local property. In rotating black holes, described by the Kerr solution, the situation becomes even more complex. The event horizon still exists, but it is surrounded by an additional region called the ergosphere. Within the ergosphere, spacetime is dragged along with the rotation of the black hole, a phenomenon known as frame dragging. Here, even light cannot remain stationary. It must move in the direction of the spin. This effect opens the door to fascinating possibilities, such as the extraction of energy from rotating black holes, as proposed in the Penrose process. Despite these added complications, the essential role of the event horizon remains the same. It is the ultimate boundary, separating regions of spacetime that are causally connected from those that are causally isolated. Once crossed, there is no communication, no signal, no message that can return. The observational confirmation of event horizons came indirectly through phenomena like X-ray emissions from accretion disks and the motion of stars near invisible objects. But in recent years, new techniques have brought us closer to direct evidence. In the year 2019, the Event Horizon Telescope released the first image of a black hole's shadow, a dark region surrounded by a glowing ring of plasma. This shadow is not the event horizon itself, but a projection of the light-bending effects near it. It is a silhouette created by the bending and capture of light in the intense gravitational field around the black hole. Its shape and size match the predictions of general relativity, reinforcing the idea that event horizons are real features of the universe. Understanding the event horizon is crucial for the larger story we are telling because it marks the point where perception and physics begin to diverge. What an outside observer sees is no longer what the infalling traveler experiences. This divide is not just theoretical, it has practical implications for how we interpret signals from near black holes, how we understand time and causality, and how we grapple with the unresolved paradoxes of modern physics. The event horizon also raises deeper questions. What happens to information that crosses it? Is it lost forever, as Stephen Hawking once suggested? Or is it somehow preserved on the horizon's surface, as proposed by the holographic principle? These questions lie at the intersection of general relativity and quantum mechanics, and they remain among the most pressing problems in theoretical physics. But for now, let us return to our journey. We have approached the black hole. We understand its structure, its origin, and the nature of the event horizon. We know that crossing this boundary will be uneventful locally, but irrevocable globally. The signals we send will never escape. The stars above will seem to accelerate. The universe itself will begin to change. As we cross the horizon and continue inward, something even stranger begins to happen. Light, warped by the extreme gravity, no longer travels in familiar paths. Our view of the universe distorts, stretches, and twists. The very act of seeing becomes surreal. To understand what we would actually observe with our eyes as we fall inward, we must now explore the strange world of gravitational lensing, the bending of light by mass. As light begins to bend and the sky above warps into unfamiliar forms, we encounter another strange consequence of gravity's power over space-time, one that alters not just what we see, but how we perceive time itself. This effect, known as gravitational time dilation, is not science fiction. It is one of the most counterintuitive and experimentally confirmed results of general relativity, and it becomes especially dramatic near a black hole. To begin with, it is helpful to recall that in Einstein's view, time is not a separate entity from space. The two are woven together into a single, four-dimensional continuum, space-time. Gravity, in this framework, does not act by pulling on objects through space. Instead, massive objects curve space-time itself, and this curvature affects not just how things move, but how time flows. The stronger the gravitational field, the slower time moves, at least from the perspective of a distant observer. This effect is subtle in everyday situations, but becomes measurable with precise instruments. For example, a clock placed on the floor will tick ever so slightly slower than an identical clock placed on a high shelf due to the difference in gravitational potential. This has been confirmed in laboratory experiments using ultra-precise atomic clocks. Gravitational time dilation also plays a critical role in the functioning of the global positioning system. Satellites orbiting Earth are farther from the planet's surface and experience less gravitational pull. Their onboard clocks run slightly faster than those on the ground. If left uncorrected, this discrepancy would lead to significant errors in navigation. Engineers must apply relativistic adjustments to ensure the system works accurately. In effect, our phones rely on Einstein's theory of time to tell us where we are. Near a black hole, this same principle holds true, but the effect becomes far more extreme. The gravitational field intensifies dramatically as one approaches the event horizon. From the perspective of a distant observer, time for someone falling toward the black hole begins to slow down more and more. The closer the falling object gets to the event horizon, the slower it appears to move. Eventually, as the object nears the event horizon itself, its motion appears to nearly freeze. The light it emits becomes increasingly redshifted, stretched to longer wavelengths as it struggles to escape the deepening gravity well. To a distant observer, the object fades from view and never quite crosses the horizon. Instead, it seems to hover just above it, frozen in time. But this is not the whole story. From the perspective of the object itself, let us imagine it is a spacecraft. None of this happens. The crew inside continues to experience the passage of time as normal. Their clocks tick as usual. Their perception of the universe remains coherent. There is no sensation of slowing down or freezing. They cross the event horizon in finite time and continue falling inward. This discrepancy reveals something profound about time. It is not absolute. There is no universal clock ticking the same for all observers. Time is relative, shaped by gravity and motion. What one observer sees as an eternity, another may experience as mere moments. This idea was revolutionary when Einstein introduced it, and it remains one of the most mind-bending consequences of general relativity. It forces us to reconsider the nature of time itself. Time is not a background constant. It is a local, physical quantity that depends on where you are and how fast you are moving. This difference between the infalling observer and the distant observer is more than just a curiosity. It has deep implications for physics, particularly in the realm of black holes. For example, consider the problem of information. If a spaceship falls into a black hole and the distant observer never sees it cross the event horizon, then where does the information about its contents go? Is it lost forever, or somehow preserved at the edge? This question touches on the famous black hole information paradox, which we will return to later. For now, it is enough to note that time dilation is not merely a visual illusion. It is a real physical phenomenon, confirmed by experiments and consistent with the equations of general relativity. Interestingly, the idea that time slows in strong gravity has found its way into popular culture. In the film Interstellar, a crew visits a planet orbiting close to a supermassive black hole. Due to the intense time dilation, a few hours on the planet correspond to many years for those waiting on the spaceship. This scenario, while dramatized, is based on real physics. The film's scientific consultant, Kip Thorne, ensured that the depiction of time dilation followed the predictions of general relativity as closely as possible. In reality, such extreme time dilation would only occur in regions very close to a black hole's event horizon, regions where gravity is at its most intense. To observe this effect directly is extraordinarily difficult, but researchers continue to explore ways to measure time dilation near massive objects. By studying the orbits of stars around the black hole at the center of our galaxy, for instance, astronomers have begun to detect relativistic effects, including small but measurable shifts in the timing and shape of their orbits. The closest we have come to observing extreme time dilation is through the study of gravitational redshift. Light emitted from near a black hole must climb out of its gravitational well, losing energy in the process. This causes the light to shift toward the red end of the spectrum. The greater the gravity, the greater the redshift. This is not a Doppler effect from motion. It is a change in the frequency of light caused by gravity's influence on time. As we continue our descent into the black hole, we are not just moving through space. We are moving through increasingly distorted time. Each moment we experience takes longer and longer to reach the outside universe. Our final signals, our last flashes of light, will arrive stretched and dimmed, perhaps never fully reaching distant observers. This growing separation between inner and outer time creates a kind of temporal isolation. The deeper we fall, the less connected we become to the rest of the cosmos. Eventually, we pass a threshold where all communication outward becomes impossible, not because something breaks, but because time itself no longer connects us to the outside world. And yet, from our own perspective, time continues smoothly. We do not notice any break. The universe above appears to speed up. The stars and galaxies outside the black hole seem to whirl faster and faster, their motions compressed into brief flashes. Eventually, we may see the entire future history of the universe unfold above us in seconds. This is one of the strangest consequences of gravitational time dilation. From within the black hole, it is possible, in theory, to witness the distant future of the universe compressed into a single visual burst. Whether this would be visible in any practical sense is uncertain. The extreme conditions near the horizon may blur or obscure such images, but in principle, the idea remains. Gravity bends not only light, but time itself. So far, we have described what happens to time as we fall into a black hole, and how this affects both observers and falling objects. We have seen that clocks do not agree, and that light changes as it climbs out of the gravitational field. But vision is more than light and time. It is geometry, it is direction, it is the shape of space. As we continue inward, the light around us begins to behave in ways that no human eye has ever witnessed. The sky twists, objects appear in unexpected places. Some vanish, others multiply. Reality itself begins to resemble a funhouse mirror, but governed not by whimsy, but by the unyielding geometry of general relativity. To understand what we would actually see as we fall deeper into a black hole, we must now examine how gravity bends light, not just in terms of frequency, but in terms of path and direction. This phenomenon, known as gravitational lensing, will reveal just how strange the view becomes as we approach the singularity. With time stretching behind us and the outside universe racing ahead, we now arrive at a deeply personal question. What would we actually see if we fell into a black hole? Not what someone else would see looking in, or what equations predict from a distance, but what the experience would feel like to us, from our own frame of reference, as conscious observers crossing the event horizon and descending into one of nature's most extreme environments. To begin, it is important to emphasize that nothing in our sensory experience would immediately alert us that we had passed the event horizon. From our point of view, local physics remains smooth. No alarms ring, no forces suddenly pull us apart. The principles of general relativity guarantee that the laws of physics behave normally, at least initially, as we fall. But that is not to say the view would be normal. Far from it. Our descent begins long before we cross the event horizon. As we draw near, the curvature of space-time begins to affect the paths of photons, particles of light, around us. This means that the direction from which light reaches our eyes changes in ways that defy ordinary intuition. Stars behind the black hole become visible, curved around its silhouette by gravitational lensing. Light from above, beside, and even from directly behind us can reach our eyes through strongly bent paths. This effect becomes more intense the closer we get. The entire sky appears to compress and wrap around the black hole. Instead of seeing the stars arranged in a familiar dome above us, we begin to see them warped into a bright ring surrounding a dark central disk, the shadow of the black hole. This shadow is not the event horizon itself, but rather the absence of light from behind it, caused by photons being either absorbed or redirected before they can escape. Gravitational lensing creates a kaleidoscopic view of the universe. Light rays curve around the black hole multiple times, forming what are known as photon spheres, regions where light can orbit the black hole in unstable loops. At certain radii, photons may circle the black hole one or more times before either falling in or escaping. This means we can see multiple images of the same star, distorted and duplicated, arriving from slightly different paths. The sky becomes layered with echoes of the universe, mirrored and smeared by gravity. One of the most remarkable features of this descent is that the black hole never appears simply as a black disk growing in size. Due to the way light bends around it, the black hole seems to remain roughly the same size in our field of view, even as we fall toward it. Instead of expanding, it appears to engulf more of the sky around it. The rest of the universe is squeezed into an ever-thinning halo of light at the edges of our vision. This phenomenon arises because of how our trajectory, combined with the bending of incoming light, determines our field of view. As we cross the event horizon, we are carried inward, along with space-time itself. Photons arriving from the universe behind us still catch up, but from increasingly narrow directions. The sky collapses into a thin, bright ring, and the blackness ahead deepens. We are now inside, and from here, everything changes. The effects of gravitational lensing become more severe. Light from the universe above us now has to fall into the black hole with us to reach our eyes. It travels curved paths through warped space-time, forming streaks and arcs instead of points. The stars no longer appear in their normal constellations. They blur and stretch, pulled into spirals and bands. Visual perception also becomes more directional. As our velocity increases, relativistic beaming begins to dominate. This is a result of special relativity. As we accelerate toward the singularity, the light ahead of us becomes blue-shifted and compressed into a narrow cone. This causes a brightening of the forward direction, while light from behind us is red-shifted and dimmed. Our field of view appears to collapse forward. The effect is not symmetrical. It is shaped by both gravity and our increasing velocity. This is more than just a trick of light. The structure of space-time itself is altering how photons reach us. What we see is not just distorted, it is a direct consequence of the geometry of the black hole. Our vision is governed not only by the positions of stars and galaxies, but by the curved paths light must follow to reach our eyes. These visual distortions are not only fascinating but also deeply informative. they tell us about the curvature of space-time. In fact, much of what we understand about black holes comes from studying how they bend light. Observatories like the Event Horizon Telescope construct images of black holes not by photographing them directly, but by tracing how light is lensed and delayed around them. The same physics that lets astronomers create black hole images on Earth is at play during our personal descent. One striking consequence of this lensing is the illusion of seeing behind ourselves. Imagine floating backward toward the black hole, facing away from it. Light that would normally miss your eyes entirely is now bent around the black hole and redirected back at you. You could, in effect, see your own back. The black hole acts like a spherical mirror that captures and redirects the geometry of space. No other region in the cosmos distorts vision in quite the same way. As we descend deeper toward the interior of the black hole, the patterns of light begin to lose meaning. The sky dims, the stars vanish, not all at once but gradually, as fewer photons find their way to us. Time and direction begin to collapse together. The past light cone, the region of space-time from which light can reach us, shrinks. There is less and less of the universe that can still interact with us. From the outside, our descent has long since ceased to be visible. To distant observers, we faded and froze near the horizon. But from our own view, the descent is ongoing. The visual world becomes dominated by dark gradients, occasional flashes, and ghost-like arcs of light, vestiges of the universe we once knew. These final views are shaped by the intricate interaction between our velocity, the curvature of space-time, and the residual light still falling in. At this point, it is worth noting that the scale of the black hole plays a crucial role in how these effects manifest. A stellar mass black hole, with perhaps a few times the mass of our Sun, has a much smaller event horizon than a supermassive black hole. This means that the tidal forces, the differential gravitational pulls across our body, would be intense even before we reached the horizon in the smaller case, potentially tearing us apart. In contrast, a supermassive black hole, like the one at the center of our galaxy, would allow us to cross the event horizon without immediately being stretched or crushed. The visual distortions, however, would occur in either case, shaped by the same underlying geometry. All of these effects, gravitational lensing, relativistic beaming, redshift and blueshift, are governed by the same physics that Einstein unveiled over a century ago. And yet, their consequences for our perception are far from intuitive. The human eye, evolved for flat spacetime and gentle gravity, is not designed to make sense of what we would see. But the mathematics allows us to predict it, simulate it, and understand it. Modern computer models use ray tracing techniques to simulate how light would move through curved space-time. These models have been used to generate the astonishing visuals seen in films, documentaries, and scientific publications. They let us visualize what the eye cannot truly comprehend. But behind every pixel of those simulations is a deeper truth. The curvature of space-time reshapes the very act of seeing. And now, as we fall ever closer toward the singularity, we must consider not just what we see, but what happens to our bodies, our instruments, and even the atoms that make us up. The black hole's gravity does more than curve light and time. It begins to stretch space itself, pulling harder at our feet than our head. As the visual world around us bends and twists under the influence of the black hole's gravity, we now begin to appreciate a phenomenon that plays a crucial role in both the science and the strange experience of falling inward. Gravitational lensing. This is not just an abstract effect seen through telescopes. It is something that shapes every photon reaching our eyes during this descent. It determines how we see the universe above, and how the geometry of space itself becomes a distorting lens. Gravitational lensing refers to the bending of light caused by the curvature of space-time around massive objects. According to general relativity, light does not always travel in straight lines, at least not in the Euclidean sense. Instead, it follows what are known as geodesics, the shortest possible paths through curved spacetime. When spacetime is bent by the presence of mass, these geodesics also curve, and so the light does too. This bending becomes noticeable when light from a distant source, like a star or a galaxy, passes near a massive object such as another galaxy, a cluster of galaxies, or, most dramatically, a black hole. The result is that light which would otherwise miss our line of sight is redirected toward us. To an observer, the distant object may appear magnified, distorted, or even duplicated. This is gravitational lensing. Astronomers have used this effect for decades as a tool to study the cosmos. In fact, some of the most compelling evidence for dark matter comes from gravitational lensing. When we observe distant galaxies being lensed in ways that cannot be explained by visible mass alone, it reveals the presence of unseen matter, matter that exerts gravitational pull even though it emits no light. In the context of our personal fall into a black hole, gravitational lensing does something even more dramatic. It transforms the very nature of the sky. Stars that should be hidden behind the black hole's bulk become visible. Their light curves around the event horizon and reaches us from unexpected angles. Some stars appear multiple times as their light follows different looping paths before arriving. These are not illusions. They are real photons traveling real paths governed by the geometry of space. The strongest lensing occurs at a specific distance from the black hole, known as the photon sphere. In the case of a non-rotating Schwarzschild black hole, the photon sphere lies at 1.5 times the Schwarzschild radius. At this radius, light can orbit the black hole in unstable circular paths. A single disturbance, like a slight deviation in direction, can cause the photon either to spiral inward and be lost, or to escape outward. This photon sphere defines the sharp boundary of the black hole's shadow as seen from outside. The shadow is larger than the event horizon itself because it includes the region where light is captured. The famous image produced by the Event Horizon Telescope in the year 2019 shows this shadow clearly, a dark, central area surrounded by a glowing ring. That glowing ring is composed of photons that have skimmed the photon sphere, bent nearly all the way around the black hole before escaping toward Earth. From our perspective, now descending past the event horizon, the photon sphere still plays a role. Even though we are now inside the region from which no light escapes outward, we can still receive light falling in. Light from the universe above us continues to rain down, although increasingly redshifted and dimmed, and that light still carries with it the effects of lensing. To understand what this looks like, imagine peering upward toward the thinning halo of the universe. The stars and galaxies appear in strange places, many compress toward a ring near the edge of your vision. As you rotate your gaze, you might find the same galaxy appearing more than once, slightly shifted. These multiple images result from photons that have taken different routes around the black hole. Some may have looped all the way around before reaching you. This duplication is not just theoretical, it has been observed in distant galaxies. In some cases, gravitational lensing by a galaxy cluster has created multiple images of a single background galaxy, arranged like petals in a flower. These are known as Einstein crosses or Einstein rings, depending on the configuration. In our case, the lensing is more intense than anything observed in the distant cosmos. The gravity of the black hole is so extreme that light paths bend by hundreds of degrees. Some photons can orbit multiple times before reaching your eyes. The result is a chaotic visual field, rich with distortions, arcs, and blurred halos. These effects depend not only on the mass of the black hole, but also on its spin. In rotating black holes, described by the Kerr metric, the paths of photons are even more complex. The black hole's rotation drags space-time around with it, a phenomenon known as frame dragging. This causes photons traveling in the direction of rotation to behave differently from those going against it. The result is an asymmetric lensing pattern. The shadow of a rotating black hole appears slightly flattened on one side and brighter along the direction of spin. Simulations of this effect have been produced by physicists and computer scientists, often with remarkable precision. One particularly well-known example is the black hole depicted in the film Interstellar. The visuals for that film were generated using equations developed by Kip Thorne and a team of visual effects experts. Their goal was not merely cinematic beauty, but scientific accuracy. What they produced was a lensing pattern so complex that even seasoned physicists learned new details from the simulations. These simulations show that lensing near a black hole does not simply distort objects. It remaps the sky. The entire celestial sphere is folded, twisted, and wrapped. You might see the galaxy core above and below you at the same time. You might see light from behind you bent forward. The idea of direction begins to lose meaning. What matters is not where an object is, but how its light travels to your eyes. Even your own body, if visible to you in the right conditions, might appear distorted. Photons bouncing off your arm or shoulder could follow curved paths before returning to your eyes, creating ghost-like or stretched images. In theory, you might even catch glimpses of your own back, depending on your position and movement. This extreme visual distortion contributes to the eerie, otherworldly nature of falling into a black hole. It is not simply dark, it is filled with strange light that behaves in ways no human has ever experienced. The eye is overwhelmed not by blackness, but by geometry. And yet, even as the universe above is refracted into an alien panorama, the brightness begins to fade. Light from the outside world becomes increasingly redshifted, its energy spread across longer and longer wavelengths. What once was visible, light becomes infrared, then microwave, and eventually radio waves. To your eyes, the sky dims. The photons still arrive, but no longer in a visible form. Eventually, the universe itself disappears, not because it has gone away, but because it can no longer reach you in a form your senses can detect. The lensing continues, but the light itself grows cold and dark. This moment marks a kind of sensory boundary. The outer universe, once distorted and fragmented across the sky, now fades into invisibility. The only remaining photons are those trapped within the black hole itself, moving inwards along with you. No light can come from below. Only above, and only briefly, does the memory of the cosmos linger. Gravitational lensing has reshaped your vision, allowed you to see impossible things, and collapsed the geometry of the universe into a sphere of surreal imagery. But even this experience has limits. The curvature continues to intensify. The effects of gravity grow not just in strength, but in difference across your body. Now, it is not only light that is being pulled in strange directions. It is you. Your head, your chest, your legs, and even your atoms are now experiencing different gravitational pulls. Space is stretching, differently in different places. The gentle distortions of vision give way to something more physical. Even as the light around you twists into surreal forms and fades into darkness, your body remains in motion, still falling, still accelerating deeper into the warped geometry of the black hole. And now, with each passing moment, the effects of gravity begin to manifest in a more physical, more personal way. No longer is the black hole only shaping light and time. It is now reshaping space itself, and with it, you. This process is known in popular science as spaghettification, a term that sounds whimsical but describes a deeply serious physical effect. The name captures the essence of what happens. An object falling into a black hole is stretched lengthwise and compressed sideways, much like a piece of spaghetti being pulled at both ends. It is the result of tidal forces, differences in gravitational pull across the length of an object. On Earth, tidal forces are responsible for the rising and falling of ocean levels. The Moon's gravity pulls slightly more strongly on the side of the Earth facing it than on the far side, causing a bulging of water. These forces are gentle on a planetary scale, but the underlying physics is the same. Gravity is not uniform across a body, and those differences cause stretching. In the context of a black hole, these tidal forces are anything but gentle. As you fall closer to the singularity, the gravitational pull on your feet becomes noticeably stronger than the pull on your head, assuming you are falling in feet first. The greater the difference between those two forces, the more your body is stretched. At the same time, gravity also compresses you in directions perpendicular to your fall, squeezing your sides inward. This effect is purely geometric. It arises not from any friction, pressure, or impact, but from the changing curvature of space-time across your own body. The closer you are to the singularity, the more extreme the difference in gravitational strength between one part of you and another. In smaller black holes, those only a few times the mass of the Sun, this stretching effect becomes deadly even before you reach the event horizon. The singularity lies so close to the horizon that the gradient in gravity is extremely steep. A human falling into such a black hole would be pulled apart violently long before crossing that invisible boundary. Muscles, bones, organs, and even molecules would be torn apart by tidal forces stronger than any material can resist. but in larger, supermassive black holes, such as the one at the center of the Milky Way, the situation is different. These giants have event horizons many millions of kilometers across, and because the singularity lies so far inward, the tidal gradient at the horizon is much weaker. In fact, you could cross the event horizon of a supermassive black hole without feeling anything unusual at all. Only as you descend further, closer to the central singularity, do the stretching forces begin to intensify. What is truly remarkable about this phenomenon is how universal it is. Everything is affected, from the largest spacecraft to the smallest atom. The forces do not depend on what something is made of. They depend only on its size, its position relative to the center of mass, and the rate at which space-time is curving. No amount of shielding, structure, or material strength can prevent spaghettification if the tidal gradient becomes strong enough. This leads to an inescapable conclusion. At a certain point, all complex structures, cells, molecules, atoms, will be pulled apart. The cohesive forces that normally bind matter together will be overwhelmed. You will not be crushed in the usual sense. Instead, you will be unraveled. The black hole does not simply destroy, it deconstructs. The mathematics of this process can be traced back to the equations of general relativity, which describe how space-time curvature changes from point to point. These equations reveal that the closer you are to the singularity, the more sharply space-time bends. The Riemann curvature tensor, a mathematical object that encodes how distances and directions change in curved space, grows without bound. The result is a tidal acceleration that increases rapidly with each fraction of a second as you fall. Physicist Andrew Hamilton, among others, has studied the internal structure of black holes and produced detailed visualizations of what this descent might feel like. His work suggests that once tidal forces reach a critical level, your body's structure is stretched into a long, narrow strand, with parts of you moving along different geodesics, separate paths through space-time. Communication between particles is severed. Information cannot travel fast enough to keep the body coordinated. In this state, the very concept of you begins to break down, not all at once, but gradually and inexorably. First, the organs stop functioning as a coherent system. Then, the molecules lose contact with one another. Eventually, even the nuclei of atoms are separated. The black hole unpacks you into your most fundamental components. One of the strange features of this process is how it unfolds over time. From your own perspective, time continues to flow normally. You do not experience anything unusual until suddenly everything is happening at once. The stretching accelerates. The signals within your nervous system cannot keep up. The process that began as a gradual elongation becomes an unstoppable collapse of structure. Outside observers, of course, do not see this. To them, you never truly fall in. You remain frozen near the horizon, a silent image, redshifted to invisibility. Your spaghettification is hidden, like everything else inside the black hole, behind the veil of the event horizon. From a philosophical perspective, this raises questions about identity, continuity, and the nature of physical systems. What does it mean for something to exist if it is being deconstructed so completely? Is spaghettification a form of destruction or transformation? Are the atoms that once formed you now part of the singularity? Do they retain any information about their previous configuration? These questions touch on deeper paradoxes about black holes, particularly the issue of information loss, which will come in later sections. But for now, it is enough to say that spaghettification represents the physical culmination of your fall. Light has failed you, time has stretched, space has turned inward, and now, even your structure has surrendered. It is worth noting that spaghettification is not just a theoretical prediction. Astronomers have observed candidate events where stars are torn apart as they pass close to a black hole. These tidal disruption events release bursts of radiation as the star's material is stretched and heated. Though on a much grander scale, they reflect the same principles. The physics that pulls apart a star is the same physics that would stretch a person. Despite the popular name, spaghettification is not a violent explosion. It is a silent process, dictated by geometry. There is no scream, no sound, only the quiet certainty of increasing gravitational difference. If one could freeze the process in time, the result would be a thin, luminous thread of particles, drawn ever closer to the center. And what lies at that center? What is the singularity that awaits? The inevitability of spaghettification leads us to a deeply human question, one that extends beyond physics and into personal experience. Could anyone actually survive a fall into a black hole? It is a question that science fiction has long entertained, often with imaginative liberties. But to examine it seriously, we must strip the question of fantasy and ground it in the physical realities of space-time, tidal forces, mass, and scale. Survival, in this context, does not simply mean avoiding immediate death. It means enduring, intact, conscious, and functioning long enough to meaningfully experience the descent, possibly even crossing the event horizon before nature's forces render survival impossible. The answer depends on a crucial and sometimes overlooked detail. Not all black holes are the same. In particular, a key variable that shapes your fate is the mass of the black hole. Black holes come in a range of masses, and this determines the size of the event horizon, the strength of gravitational gradients, and the intensity of tidal forces. A stellar mass black hole, formed from the collapse of a massive star, has a radius of only a few kilometers. In such compact black holes, the tidal forces near the event horizon are extraordinarily steep. As you approach, the difference in gravitational pull between your head and your feet becomes large enough to destroy you well before you cross the horizon. No part of your body, or any spacecraft, could withstand the forces involved. But supermassive black holes, like the one at the center of the Milky Way, are a different story. With millions, or even billions of times the mass of our Sun, they have event horizons that can stretch millions of kilometers across. The larger the black hole, the weaker the tidal forces at the horizon. In these cases, you could theoretically cross the event horizon without being torn apart, at least not immediately. Imagine descending towards such a massive black hole in a specially designed spacecraft. You feel no pull, no shaking, no sudden transition. You do not see the event horizon as a physical surface. And yet, with each moment, your distance from the singularity decreases. Time, from your perspective, continues to pass normally. Gravity inside the ship feels consistent. For all practical purposes, it would be impossible to detect when you have passed the horizon, except by knowing that escape is now impossible. This leads to an unexpected truth. Survival inside a black hole, at least temporarily, is possible. Your body and mind could remain intact. You could observe, measure, and reflect, even send signals outward, though those signals would never escape. It is only as you approach the central singularity that the tidal forces would become strong enough to destroy you. In a supermassive black hole, you could survive seconds, minutes, or perhaps longer before reaching that fatal point. In this sense, survival becomes a question of time and scale. How long do you remain intact? How far inward can you travel before the physics of the singularity overtakes you? And what can you learn during that time? This idea has fascinated physicists and science communicators alike. Some have proposed using black holes as observational platforms, imagining probes that could descend past the horizon, transmitting data back until the point of signal loss. Others have speculated on what a conscious observer might perceive and whether any traces of those perceptions could be encoded in Hawking radiation or other emergent effects. These questions often border on speculative physics, but they are rooted in real theoretical frameworks. Physicist Andrew Hamilton, for example, has modeled what it would be like to fall into different classes of black holes. His work suggests that while death is ultimately inevitable, the experience could vary dramatically depending on the black hole's mass and spin. In some cases, survival beyond the event horizon could last long enough for meaningful observations, at least from the falling observer's frame of reference. This line of inquiry leads to one of the more subtle but profound aspects of black hole physics: the nature of reference frames. In general relativity, all reference frames are locally valid. That means that from the perspective of the falling observer, physics behaves normally up to the point of singularity. This concept, called the equivalence principle, guarantees that free fall into a black hole, even past the event horizon, is not locally distinguishable from free fall in any other gravitational field. It is only when you try to compare your frame with an outside one, say, someone observing you from far away, that contradictions begin to appear. This is not because the physics is inconsistent, but because the geometry of space-time separates your paths. You are now causally disconnected. No signal, no particle, no bit of information can reach back across the horizon. So while you may survive survive the fall for a time, your experience becomes completely private. No observer in the outside universe can confirm what you see, what you feel, or even that you continue to exist. In this sense, survival is deeply subjective, real to you, but inaccessible to everyone else. There is also the question of the nature of the singularity itself. While general relativity predicts that you will be destroyed by infinite curvature at the center, it also admits that this is a place where the theory breaks down. Singularities represent not physical structures, but the limits of our current models. What actually happens at or near a singularity is a mystery. Some theorists believe that a complete quantum theory of gravity might one day replace the singularity with something more structured, a core where space and time continue in some altered form. If that turns out to be true, it could reshape the answer to our central question. Instead of being inevitably destroyed, a falling observer might encounter a new regime of physics, a domain of quantum space-time where new behaviors emerge. But this remains purely theoretical. No current theory can fully describe the interior of a black hole, especially near the singularity. From a biological and engineering standpoint, survival also hinges on radiation, heat, and stability. Black holes are not empty. The region around them can be filled with high-energy particles, magnetic fields, and intense radiation from accreting matter. A spacecraft attempting to approach a black hole would need protection against these hazards long before reaching the event horizon. Once inside, the environment is quieter, but no less deadly in the long term. Without any possible return, the journey is one way. And yet, from a physicist's point of view, the idea of survival is not dismissed out of hand. It is examined carefully, mathematically, with full awareness of both relativistic principles and the limitations of our theories. In that light, the possibility of surviving for a finite time inside a black hole is not just plausible, it is expected, especially for sufficiently massive black holes. But as we fall further, the clock is ticking. Not the external clock, whose time has long diverged from ours, but the internal one, the time marked by our own heartbeat, breath, and thoughts. And with each beat, we move closer to the core of the black hole, the singularity where space-time curvature becomes infinite, where classical physics ends, and where no known theory can yet fully describe what occurs. We have seen what we might experience on the way in: the distortion of light, the stretching of space, the warping of time. We have considered what survival means under these conditions and for how long it might last. But what awaits at the center is something else entirely. As we continue falling deeper into the gravitational well of the black hole, we approach the one threshold that has defined so much of our discussion, the event horizon. It is the boundary between what lies within and what remains observable from without. And yet, despite all the cosmic weight the event horizon carries, its association with mystery, with finality, even with destruction, the most surprising thing about it may be what does not happen when we cross it. Contrary to popular depictions, you would feel nothing unusual as you pass through the event horizon of a sufficiently massive black hole. There is no bump, no jolt, no shimmer of light or blast of energy. The crossing itself is entirely uneventful from your own perspective. You would not even know it occurred unless you had pre-calculated your distance from the center and had an onboard clock ticking away your trajectory. This is not an artistic exaggeration. It is a direct consequence of the equivalence principle in general relativity. According to Einstein's theory, all the laws of physics must remain locally the same in any freely falling frame of reference. That means that for a person falling freely through space-time, whether near Earth or inside a black hole, the local experience of physics remains normal. No gravitational force is felt, because gravity in general relativity is not a force pulling you downward, but a curvature of the paths through space-time. You are simply moving along a geodesic, the natural path through curved space, and crossing the event horizon does not interrupt that path. This leads to a subtle but crucial distinction between local experience and global structure. Locally, your clocks tick as usual. Your instruments function normally, light from within your spaceship travels in the usual way, but globally, something irreversible has happened. You are now in a region of space-time from which no signal, no particle, and no information can escape back to the external universe. All light cones, the regions of space-time from which light or any influence can reach you, are now tilted inward, pointing toward the singularity. In simpler terms, every direction you might travel, every effort you might make to turn around or climb out, leads only deeper inward. Even if you could accelerate at unimaginable speeds, it would make no difference. The geometry of space-time itself is such that outward no longer exists as a viable direction. Escape is not a matter of energy or willpower, it is a matter of geometry. From the outside, however, things appear dramatically different. An external observer watching your fall would never see you actually cross the horizon. Instead, they would see your image slow down, dim, and redshift toward infinity. Your light becomes stretched into longer and longer wavelengths, and the time between signals grows ever longer. Eventually, your final signals would be stretched into radio waves, then into wavelengths too long to detect. From their perspective, you appear to freeze at the edge, never quite gone, yet no longer visible. This strange duality, that you continue inward freely while others see you as suspended eternally at the edge, is not a paradox. It is a feature of relativistic physics. Time itself is not absolute. Different observers can legitimately perceive the same sequence of events in vastly different ways. For the falling observer, the journey continues naturally. For the outside universe, it comes to a halt at the boundary. This difference in perspective is not merely academic. It plays into deep questions in physics about what happens to matter and information that falls into a black hole. Stephen Hawking's early work suggested that information might be lost forever, violating fundamental rules of quantum mechanics. Later theories proposed that this information might somehow be preserved on the event horizon, encoded holographically in ways we do not yet fully understand. But setting aside those future paradoxes for now, let us return to the experience itself. Inside the event horizon, the coordinates of space and time switch roles in a very literal way. Outside the black hole, you can choose where to go in space: left, right, up, down, while time flows inexorably forward. Inside, one spatial direction, toward the singularity, becomes as inevitable as time was outside. In fact, it is time. Just as you cannot choose to go backward in time, you cannot choose to move away from the singularity. It lies in your future, not merely your location. This makes the event horizon a boundary, not just in space, but in causality. It is the threshold where freedom of motion collapses into determinism. No matter your intentions, no matter your trajectory, your future now includes the singularity. There is no maneuver that will change that fact. Even so, you can still function for a while. Your instruments can measure local conditions. You can look around and observe, although the light reaching you from outside grows ever dimmer and redder. The universe beyond begins to recede, not physically, but causally. You may see the stars of the Milky Way compressed into a glowing ring, or observe ancient light that began its journey across the cosmos billions of years ago. From your perspective, time outside the black hole appears to accelerate. Events far in the future might play out in moments as you descend. But these observations become fewer and dimmer as you fall further. The photons from the outside universe become less energetic. Eventually, they cease to fall inward quickly enough to reach you before you pass beyond the point where they could intersect your path. The outside world fades, not from view, but from interaction. Yet for now, the environment remains deceptively calm. If you were inside a supermassive black hole, tidal forces at the event horizon would be mild. There would be no immediate stretching or compression. The blackness ahead would remain featureless, silent. Only your knowledge of physics would remind you that you are now inside a region with fundamentally different rules. Rules that prohibit any return, that trap light, that bend the very meaning of direction. What is most remarkable is how silent the transformation is. There is no external marker of what has changed, no event that announces your entry. It is only through theoretical understanding and abstract calculation that we can even define the boundary. And yet, that boundary has consequences of the highest order. It is not only a line in space, but a frontier in knowledge. In the decades since Einstein's theory first revealed the possibility of such boundaries, physicists have debated their implications. Are they real in the sense that we understand material objects to be real? Or are they mathematical artifacts, useful for understanding the behavior of equations, but with no physical existence? The observational evidence, especially from black hole candidates, gravitational waves, and images like those from the Event Horizon Telescope, strongly supports the reality of event horizons. They are not just metaphors, they shape what can and cannot happen in the universe. In fact, they define the very nature of causality. If the universe has boundaries beyond which no signal can return, then it has regions permanently severed from interaction with us. What happens inside the event horizon stays inside. This realization forces us to reconsider how we define knowledge, observation, and prediction. In classical physics, knowing the present allows you to calculate the future. But with black holes, whole regions of space-time are hidden forever from view. Still, within the black hole, your journey continues. The horizon has passed, unnoticed. The path forward is now inward, always inward. The geometry ensures that your destination is the singularity. And while the singularity itself is not a place in space, but a limit in space-time, it lies in your future as surely as tomorrow lies ahead of today. From this point onward, each moment brings stronger curvature, deeper time dilation, and greater tidal effects. The black hole begins to assert itself not just as a warper of light and time, but as an engine of fundamental change. What you see narrows, what you feel intensifies, what you understand begins to dissolve into abstraction. As we drift inward beyond the event horizon, past the invisible boundary where all outward paths point inevitably toward the singularity, something astonishing begins to unfold above us. The blackness that swallowed the sky slowly yields to a subtle, almost haunting transformation. The shrinking sliver of visible universe no longer behaves as we expect. Instead, it begins to move in reverse, not physically, but temporally. From our unique vantage point deep inside the black hole's curved space-time, we begin to witness an illusion that challenges our most fundamental assumptions about time, motion, and causality. This surreal effect emerges from the immense gravitational time dilation we discussed earlier, now taken to the extreme. Outside the black hole, time continues as normal for distant observers. Stars evolve, galaxies collide, civilizations rise and fall. But from our own perspective, accelerating inward toward the singularity, our clock is ticking differently. The deeper we fall, the faster the external universe appears to move. The events in the cosmos above us begin to unfold at an accelerated rate. Eventually, this time difference becomes so vast that we begin to perceive the future of the universe playing out before us, like a time-lapse film projected onto the thin ring of sky still visible from inside the black hole. Supernovae erupt in rapid bursts, galaxies twist and fade, cosmic structures evolve over billions of years, compressed into mere seconds from our frame of reference. This strange acceleration is not just metaphorical, it is a direct consequence of the warping of space-time. To a stationary observer far from the black hole, your descent may seem to take forever, with your last transmission stretched across eternity. But for you, events far into their future are accessible in your present. The longer you fall, the more you see. Some theoretical models even suggest that you could, in principle, witness the heat death of the universe. When all thermodynamic energy has dissipated, stars have faded, and only blackness remains. From your perspective inside the black hole, that terminal stage of cosmic evolution may arrive before you reach the singularity. But this is not the strangest part. As your view compresses into the final angles of sky, something unexpected begins to happen. The universe does not just speed up, it begins to appear as though it is running in reverse. Stars that once aged now seem to unage. Explosions shrink back into points. The flow of time, as seen from your limited visual cone, begins to invert. This reversal is not actual time travel, of course. It is a perceptual artifact created by the severe relativistic differences between your frame and the external universe. The light that reaches you has been stretched, looped, and curved by both the gravitational field and the collapse of space-time itself. To understand this, we need to consider the way light behaves in a highly curved region. Every photon you see has traveled a path through warped space-time. But now, as the geometry closes in around you, fewer and fewer paths remain open. Only photons from extremely distant events, ones that took place very far in your past but very far in their future, can reach your eyes. The visual result is profound. You may witness what seems like the unraveling of the universe. Distant galaxies retreat into their younger forms. Bright stellar remnants fade into progenitor stars. Cosmic structures appear to reverse their evolution. The arrow of time, so central to our understanding of reality, seems to bend back upon itself. This inversion is purely observational. From the perspective of each external object, time continues forward. Their processes, their thermodynamics, their clocks all move ahead in their own frames. But the signals reaching your eyes have traveled such complex, time-dilated routes that their sequence appears reversed. The effect is reinforced by gravitational lensing. As the light is bent around the black hole, some of it loops back multiple times before finally reaching your eyes. These looping paths cause further temporal distortion, since light from different epochs may arrive simultaneously or out of order. Events that occurred at different times may be visible all at once, layered over each other like reflections in a cracked mirror. And still, the window grows smaller. The sky above contracts into a dimming ring. The rest is consumed by the surrounding blackness. It is not merely dark, it is absent. The paths through space-time that would once have delivered light from those directions no longer exist. Space has become so curved that only a narrow cone of light can reach you, and even that cone is fading. The visual field becomes surreal. It is not black, it is distorted. It is full of echoes and ghosts, events compressed and distorted by gravity. There is no stable perspective. What you see depends entirely on where you look and how long you have been falling. The very notion of direction becomes suspect. Up, down, left, right, they lose their meaning. Only inward remains coherent, and even that is not quite what it seems. In these moments, as the singularity draws closer, you may begin to reflect on what you are really seeing. Is it a glimpse of the end of time? Is it a relic of the past, or a preview of what lies ahead? Perhaps it is both. Or neither. In the language of general relativity, the singularity is not a point in space, but a boundary in time. It is not that you are heading toward a location, you are heading toward an event in the structure of the universe. And yet, remarkably, you remain conscious, at least for a brief time longer. You are not crushed instantly. The fall continues. The light fades. This concept of watching the universe accelerate and then appear to reverse is not merely poetic. It arises directly from the mathematics of curved space-time. It has been explored in simulations and models by physicists attempting to understand the final visual experiences of an observer falling into a black hole. In some ways, it represents the ultimate irony. As you approach the most violent and unknowable region in the cosmos, you are granted a vision of the cosmos itself, its distant future, its acceleration, its entropy, and perhaps even its conclusion. And this vision, though brief, is one of the most extreme vantage points in physics. No telescope, no probe, no observation from outside can replicate what you see. It is the privileged view of the infaller, the one who chose to cross the horizon and face the unknown. But the time for vision is nearly over. The photons have done their best to tell the story of the universe, but now they fail. Their sources are too far. Their paths are too distorted. The geometry is closing in. There is no more light, no more outside. Only the interior remains. As the light from the universe fades and the last visual fragments of reality dissolve into darkness, we are left with a profound and unsettling question. What lies ahead now that we are past the event horizon and falling toward the singularity? At this depth, perception gives way to theory. No traveler has returned to describe the experience, and no telescope can penetrate this far. All we have are the equations of general relativity and the increasingly abstract models built from them. And yet, those equations offer powerful insights. They reveal a domain where the very concepts we rely on, space, time, direction, even before and after, begin to lose their familiar meaning. The path toward the singularity is not just a journey through space. It is a journey into the breakdown of coordinates. To understand this, let us revisit how Einstein's general theory of relativity treats the geometry of space-time. The core idea is that gravity is not a force in the traditional sense. Instead, it is the manifestation of space-time curvature. Mass and energy tell space-time how to bend, and curved space-time tells matter how to move. These relationships are expressed mathematically through a set of equations called the Einstein field equations. When applied to a spherically symmetric, non-rotating mass, These equations yield the Schwarzschild solution, the simplest black hole geometry. From the outside, this geometry seems straightforward enough. Space is curved, time slows near the event horizon, and nothing escapes once it crosses. But inside the event horizon, the very structure of the coordinates used to describe spacetime begins to shift in a fundamental way. Outside the black hole, we think of time as a forward-flowing dimension and space as a three-dimensional arena in which we can move freely. If we describe spacetime using the Schwarzschild metric, the time coordinate behaves normally. It increases as an object moves forward in time, and the radial coordinate, representing distance from the center, decreases if we move inward. But once we cross the event horizon, these roles reverse. The radial coordinate becomes time-like, and the time coordinate becomes space-like. In practical terms, this means that moving closer to the singularity is no longer something you can choose to do or not do. It is not like walking from one place to another. Instead, it becomes as unavoidable as moving forward in time. The singularity lies in your future the same way tomorrow does. You cannot remain still. You cannot turn around. Every possible path leads inward. This reversal has strange consequences. For one, it collapses all freedom of movement. Inside the horizon, you are not simply falling toward the center, you are being carried there by the geometry of spacetime itself. Even if you were to fire your engines at full power in the opposite direction, you would still move inward, because inward is now the only direction that time itself flows. All future-directed paths lead to the singularity. And yet, while this situation seems dire, the geometry remains smooth. The singularity does not reside at the event horizon itself. That region, as we have already seen, is locally benign. It is only as you approach the center, what the Schwarzschild coordinates label as zero radius, that the curvature of spacetime increases without bound. The Riemann curvature tensor, which quantifies how much spacetime bends, grows infinitely large. This is not just a physical extreme, it is a mathematical one. This infinite curvature signals a breakdown in the theory. It means that general relativity, though exquisitely successful in describing planets, stars, galaxies, and even the behavior of black holes from the outside, ceases to provide meaningful answers at the singularity. The coordinates used to describe spacetime become undefined. The equations produce infinities, quantities that cannot be interpreted in a physical way. It is important to stress that this singularity is not a thing in the usual sense. It is not a dot of mass at the center of the black hole, nor is it a solid object. It is a region where the very concept of spacetime ceases to exist in the way we understand it. It is the place where distances shrink to zero, where the future ends, and where predictability vanishes. Roger Penrose and Stephen Hawking studied these ideas in great detail during the 1960s and 1970s. They developed a series of mathematical theorems, now known as the Penrose-Hawking singularity theorems, that showed under very general conditions the formation of singularities is inevitable in both collapsing stars and in the early universe. In other words, if general relativity is correct, then singularities are not rare exceptions. They are built into the structure of the cosmos. These theorems do not describe what the singularity is, only that it must occur. They show that any massive object collapsing under its own gravity, if no force intervenes to halt the collapse, must eventually reach a point where spacetime curvature becomes infinite. But they stop short of describing the singularity's nature. That remains unknown. Some theorists believe that quantum gravity, the as yet undiscovered theory that unifies general relativity with quantum mechanics, may one day resolve the singularity. In this hypothetical theory, the infinities that plague current equations might be replaced with a finite structured core, perhaps a quantum bridge or a new kind of spacetime foam. Loop quantum gravity, string theory, and other approaches are actively exploring this idea. But so far, no definitive answer has emerged. For now, the singularity remains a boundary, not just in space or time, but in knowledge itself. It is the point where our best theories stop working, where cause and effect lose their grip, where physics becomes metaphysics. And yet, from our infala's perspective, the journey continues. As we approach the singularity, clocks stop making sense. Distances lose meaning. Every reference point collapses into one. What once seemed like a direction, downward, inward, forward, now merges into a single, unescapable fate. If you were somehow still conscious at this stage, your ability to sense or interpret anything would be gone. The light has faded, the structure has broken down. The geometry around you no longer supports distinct locations or motions. You have reached the interior of a black hole, not in the sense of standing in a room, but in the sense of entering a realm where concepts like room no longer apply. In classical general relativity, this is the end of the story. The singularity lies ahead, and nothing more can be said. But if modern physics is to go further, it must answer a deeper question. What happens next? Is the singularity truly the end, or is it the gateway to something else? Could quantum gravity provide a new chapter, one in which space-time continues in some novel form? Could information survive? Could space be reborn? These are not questions we can yet answer, but they are the frontier of current research. And to approach them, we must begin to consider effects that transcend general relativity, effects that come not from the smooth geometry of space-time, but from the jittery, probabilistic rules of the quantum world. As we reach the singularity, we arrive not only at the center of a black hole, but at the edge of theoretical physics itself. The singularity, it is where all trajectories within a black hole ultimately lead. No matter your mass, velocity, or intentions, once inside the event horizon, your future ends there. Yet for all its gravitational dominance, the singularity remains one of the most elusive and mysterious elements in modern physics. We know it must exist, our equations demand it, but we do not know what it is. We cannot see it, measure it, or describe it in physical terms using the tools of general relativity alone. It stands not merely as a feature of space-time, but as a fundamental failure of our understanding. In the language of general relativity, a singularity is a point, or more accurately, a region where space-time curvature becomes infinite. The density of matter becomes infinite, the gravitational field becomes infinite, and distances shrink to zero. At such extremes, the predictive power of the Einstein field equations breaks down. They yield not definite answers, but infinities, mathematical signs that our model has reached its limit. But this breakdown is not a flaw in calculation. It is a signal, an indicator that the theory has been pushed beyond the realm where it applies. General relativity is a classical theory, and like all classical theories, it begins to unravel when quantum effects become significant. Just as classical mechanics fails to describe atoms, and electromagnetism fails to explain the photoelectric effect without quantum theory, general relativity fails to describe the heart of a black hole without a quantum theory of gravity. So what is the singularity, really? Roger Penrose was one of the first to formalize its inevitability. In the early 1960s, he introduced a powerful mathematical concept called a trapped surface, a region of space-time from which all light rays, even those directed outward, are drawn inward. His theorems, combined with later work by Stephen Hawking, showed that under very general conditions, the formation of a singularity is unavoidable during gravitational collapse. These results did not depend on spherical symmetry or particular matter distributions. They were robust and general. They told physicists that singularities were not mere curiosities. They were built into the fabric of the cosmos. Stephen Hawking extended these ideas into the realm of cosmology. He showed that the universe itself may have begun with a singularity, an initial point where the same breakdown occurs. In both the beginning and the end, singularities appear as the boundary conditions of space-time. They mark the moments where classical physics yields to something deeper. But describing that something deeper remains a formidable challenge. Physicists believe that to truly understand the singularity, we must develop a theory that unifies general relativity with quantum mechanics, a theory of quantum gravity. Such a theory would not only describe how space-time behaves under extreme conditions, but also how it fluctuates, evolves, and perhaps even gives rise to particles and forces. Several competing approaches attempt to fill this gap. String theory proposes that the fundamental constituents of nature are not point-like particles but vibrating strings, whose modes of vibration correspond to different particles. In this framework, gravity arises naturally, and singularities may be smoothed out by the extended structure of strings. Another approach, loop quantum gravity, suggests that space itself is quantized, made up of discrete loops or chunks of space-time. These loops could, in theory, prevent infinite compression. Instead of reaching zero volume and infinite density, the collapsing matter might reach a minimum size and then rebound, possibly giving birth to a new region of spacetime, a new universe. These ideas are speculative, but they offer tantalizing possibilities. If the singularity is not truly a point of infinite density, but a gateway to something else, then the interior of a black hole may contain more than destruction. It may be a transitional phase, a transformation, or even a bridge. Some models suggest that the matter falling into a black hole could eventually emerge through a white hole, the time reverse of a black hole, from which matter emerges but nothing can enter. Others speculate about wormholes, tunnels through space-time that connect distant regions or even separate universes. These ideas are supported by solutions to Einstein's equations, such as the Einstein-Rosen bridge, though whether they can exist stably in reality is still debated. In all these proposals, the singularity plays a central role, not just as an endpoint, but as a place where new physics must begin. It is the ultimate laboratory for testing our theories, but it is also the ultimate veil. No signal can escape from beyond the singularity, and no experiment can probe its nature directly. Our understanding remains theoretical, grounded in mathematics and constrained by the limits of observation. Even so, singularities affect the universe in measurable ways. They shape the structure of black holes, influence the motion of stars, and generate the gravitational waves we now detect from colliding black holes. The signal that reached Earth from such a collision in the year 2015 was a direct result of two singularities spiraling into each other, a cosmic event so violent that it shook space-time itself. These signals do not reveal the singularities directly. What they show is the effect of gravity just before the collision, but they confirm that the equations describing the path to singularity are accurate, at least up to that point. Whatever lies beyond remains hidden. This raises profound philosophical questions. If singularities are truly unobservable, if no information can escape from them, can we ever claim to know what happens there? Is physics limited to what can be measured, or can we describe realities beyond observation through mathematical inference? Stephen Hawking wrestled with this dilemma throughout his career. In his later work, he speculated that perhaps the singularity could be avoided if quantum effects cause space-time to bounce. He also proposed that the boundaries of black holes might encode information about everything that falls in, a radical idea that would become the basis of the holographic principle. According to this idea, the three-dimensional interior of a black hole might be described entirely by data encoded on its two-dimensional surface, the event horizon. This concept, developed further by physicists like Gerard 't Hooft and Leonard Susskind, suggests that the singularity might not destroy information after all. It may be preserved in some form, smeared across the boundary. If true, this could resolve one of the great paradoxes in physics, the question of whether information is lost forever in black holes. But even in this framework, the singularity remains a mystery. It is not eliminated, only reinterpreted. For now, our understanding of the singularity remains incomplete. It is the place where equations explode, where paths end, and where thought experiments stretch toward their limits. And yet, despite its inaccessibility, it may hold the key to the next great revolution in physics. Just as Newtonian mechanics gave way to relativity and quantum theory, perhaps our current models will give way to something new, something that not only explains black holes, but unites all the forces of nature into a single coherent framework. Until that day comes, the singularity remains a riddle in the dark. It is not merely a destination, but a question, a challenge posed by the universe to those who seek to understand it. And if black holes do not last forever, if they evaporate over time, as Stephen Hawking once proposed, then the singularity may not be the end after all. It may be a chapter in a longer story, one where black holes shrink, vanish, and leave behind not mystery, but meaning. If the singularity represents the innermost mystery of a black hole, an ultimate collapse of space, time, and knowledge, then the concept of Hawking radiation challenges the finality of that collapse. It asks us to imagine a very different black hole story, one not of eternal imprisonment and unbreakable boundaries, but of slow, inevitable fading. What if black holes do not last forever? What if, over cosmic timescales, they radiate away their mass, shrink, and vanish? This idea did not arise from general relativity. It came from a confrontation between gravity and quantum mechanics, the two towering pillars of modern physics that even today refuse to fit easily together. Where general relativity describes the smooth, continuous curvature of space-time, quantum mechanics tells us that the universe is fundamentally granular, filled with probabilities, uncertainties, and fluctuations. For decades, these two theories worked remarkably well within their respective domains. General relativity explained the motion of planets, the expansion of the universe, and the behavior of stars and black holes. Quantum theory explained atoms, subatomic particles, and the dynamics of fields at the smallest scales. But black holes presented a challenge that required both theories to speak at once. In the early 1970s, Stephen Hawking, then a young physicist at the University of Cambridge, set out to explore the implications of quantum theory near the event horizon of a black hole. Building on earlier work by Jacob Bekenstein, who had proposed that black holes possess entropy, a measure of disorder, Hawking wanted to understand how black holes interact with quantum fields. What he discovered was revolutionary. Using techniques from quantum field theory in curved spacetime, Hawking showed that black holes are not perfectly black. They emit a faint radiation, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, tiny, random disturbances in the quantum vacuum. To understand how this works, we must recall that the vacuum in quantum theory is not empty. It is a seething landscape of virtual particles, pairs of particles and antiparticles that pop into existence briefly and then annihilate, borrowing energy from the vacuum on timescales permitted by the uncertainty principle. Normally, these virtual pairs recombine almost immediately, leaving no trace. But near a black hole's event horizon, something strange can happen. If a virtual particle pair forms right at the boundary, it is possible for one particle to fall into the black hole while the other escapes. The escaping particle becomes real. It is now observable and carries energy away from the black hole. The particle that falls inward has negative energy relative to the outside universe. The result is a net loss of mass for the black hole. Over vast timescales, this process leads to the gradual evaporation of the black hole. At first glance, this seems impossible. How can something as powerful and massive as a black hole lose energy, let alone disappear? But the mathematics is clear. Hawking's calculations showed that the temperature of this radiation is inversely proportional to the mass of the black hole. That means the smaller the black hole, the hotter it becomes, and the faster it radiates. In contrast, supermassive black holes radiate extremely slowly, their temperatures close to absolute zero. For stellar mass black holes, the radiation is negligible. It would take longer than the current age of the universe for one to evaporate meaningfully. But as the black hole shrinks, the rate of evaporation accelerates. Eventually, in its final moments, the black hole would become incredibly hot and rapidly shed its remaining mass in a burst of radiation. This theoretical result turned black hole physics on its head. It meant that black holes are not permanent prisons, but temporary structures. Given enough time, they can vanish entirely. More than that, Hawking radiation raised profound questions about the nature of information. If a black hole evaporates completely, what happens to the information about everything it has consumed? In quantum mechanics, information is never truly lost. The evolution of a system is unitary, meaning that the past and future are connected through reversible processes. Even when particles collide, scatter, or decay, the information about their initial states remains, at least in principle, encoded in the outcome. This principle lies at the heart of quantum theory. But if a black hole swallows matter and then disappears through Hawking radiation, with that radiation appearing thermal and random, it seems that information has been lost. This contradiction came to be known as the black hole information paradox. For decades, the paradox remained unresolved. Hawking himself initially argued that information was indeed lost, a conclusion that many found troubling. It seemed to violate the core tenets of quantum physics and suggested a breakdown of predictability in nature. Other physicists, including Leonard Susskind and Gerard 't Hooft, pushed back. They proposed that the information might be encoded in subtle correlations within the Hawking radiation, that it was not truly lost but scrambled. These ideas eventually evolved into what is now known as the holographic principle. The holographic principle, inspired by insights from black hole thermodynamics and later supported by developments in string theory, proposes that all the information contained within a volume of space can be represented on the surface that encloses it. In the case of a black hole, the information about everything it has consumed might be stored not in the interior, but on the event horizon itself. If this principle is correct, then Hawking radiation does not destroy information. Instead, the radiation carries away encoded data about the black hole's contents, though in a highly entangled and complex form. The black hole slowly evaporates, but nothing fundamental is lost. This idea has gained increasing support, particularly with the development of the anti-de Sitter conformal field theory, ADS-CFT correspondence, a theoretical framework that suggests certain spacetimes can be fully described by a quantum theory on their boundary. While our universe is not exactly of the anti-de Sitter type, the principle offers a tantalizing path forward in reconciling gravity and quantum mechanics. Eventually, even Hawking revised his position. In the early 2000s, he conceded that information might indeed be preserved in black hole evaporation, though he did not provide a detailed mechanism. The debate remains active, but the consensus has shifted toward information conservation. So what does all this mean for someone who falls into a black hole? From your perspective, the story remains the same. You cross the horizon, fall inward, and approach the singularity. But from the point of view of the universe, something else is happening. The black hole that consumed you is shrinking. Over trillions upon trillions of years, it will emit more and more radiation, growing hotter and smaller until it finally disappears. And then the question becomes, what, if anything, is left behind? Some theories propose a final remnant, a tiny, stable object that holds the remaining information. Others suggest that the information has already leaked out through the radiation itself. Still, others imagine that a new region of spacetime might emerge, a kind of rebirth from the ashes of the old. In all cases, the simple idea of a black hole as an eternal object has been replaced by a dynamic quantum mechanical reality. Black holes may be born, grow, decay, and die, leaving behind traces, ripples, and perhaps even new beginnings. Stephen Hawking's work on this topic earned him global recognition. It connected black holes to thermodynamics, quantum theory, and the fate of the universe. His insight revealed that black holes are not exceptions to the laws of physics, but bridges between its deepest principles. And so, as we continue our journey, we now see that the story does not end with the singularity. There is a future beyond it, one shaped not just by gravity, but by radiation, entropy, and the interplay of the quantum world with the geometry of space and time. But this new understanding brings its own puzzles. If black holes radiate, what exactly happens at the event horizon? Is it smooth and uneventful, as general relativity claims? Or is it more dramatic, hiding violent quantum effects that tear apart everything crossing the boundary? If black holes can evaporate and radiate, as Stephen Hawking's theory proposes, and if information is somehow preserved during this process, then the black hole begins to resemble a thermodynamic object, one governed by entropy, temperature, and quantum behavior. But this shift in perspective does more than clarify the nature of Hawking radiation. It also stirs up a deep and disconcerting conflict, one that forces us to question whether the event horizon is truly as smooth and benign as general relativity claims. According to Einstein's theory, an observer falling freely across the event horizon of a sufficiently massive black hole would notice nothing special. The horizon is not a wall or surface in any tangible sense. It is simply a coordinate boundary, a point in space-time where the escape velocity exceeds the speed of light. The curvature of space-time, while increasing, is not severe enough to produce any dramatic local effects at the horizon itself. This idea is supported by what is known as the equivalence principle, a foundational tenet of general relativity. The principle states that locally, the effects of gravity are indistinguishable from those of acceleration. In a freely falling frame of reference, the laws of physics should appear exactly as they do in flat spacetime. No spikes in energy, no sudden changes, no drama. But if black holes evaporate and information must be preserved in the outgoing radiation as demanded by quantum theory, then something else may be going on. In 2012, a group of physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that triggered one of the most heated debates in theoretical physics. Their work introduced what is now known as the firewall paradox. At its heart, the paradox is a challenge to reconcile three deeply held assumptions. First, that quantum mechanics is unitary, meaning information is not lost. Second, that general relativity is locally valid, meaning a falling observer experiences nothing unusual at the event horizon. And third, that the outgoing Hawking radiation is entangled with the interior of the black hole in a way that preserves this information. The AMPS team, named after the initials of the four authors, argued that these three ideas cannot all be true at once. To see why, consider how Hawking radiation is believed to work. Each outgoing particle is thought to be entangled with a partner particle that falls into the black hole. This entanglement is crucial. It ensures that the radiation forms a pure quantum state, preserving the coherence of the system. But if the black hole has been radiating for long enough, then earlier radiation must also be entangled with the new radiation to preserve unitarity and ensure that information escapes. Now here's the problem. Quantum theory does not allow for a single particle to be fully entangled with two different systems at the same time. This is known as the monogamy of entanglement. If an outgoing Hawking particle is entangled with both its interior partner and with the earlier radiation, then something must break. The AMPS solution, one of the entanglements must be severed. And if it's the entanglement between the outgoing particle and its interior partner, then quantum theory predicts that this particle is in a highly excited state. In other words, the region near the event horizon is not empty. It is filled with high-energy quanta, a wall of fire. For the falling observer, this would be catastrophic. Instead of drifting peacefully across the horizon, you would be vaporized by a searing wall of energy. The equivalence principle would be violated. The event horizon would no longer be a benign boundary. It would be a place where space-time breaks down violently. This conclusion sparked intense debate. Many physicists were unwilling to accept the idea of a firewall. It seemed to contradict everything general relativity had taught about black holes, and it undermined the smooth structure of space-time that had been confirmed in so many other regimes. Alternative proposals soon followed. Some theorists suggested that quantum gravity might somehow preserve entanglement without triggering a firewall. Others proposed that information might be stored in subtle correlations on the horizon, avoiding the paradox altogether. One suggestion, known as complementarity, argued that the conflict is only apparent. What one observer sees outside the black hole is different from what the infalling observer experiences, and the two can never compare notes. Another avenue of thought explored soft hair, a term introduced by Stephen Hawking and collaborators Malcolm Perry and Andrew Strominger. This idea proposes that black holes possess subtle quantum degrees of freedom, soft photons or gravitons, that can encode information on the horizon without requiring extreme energy densities. These soft hairs could carry away information without invoking firewalls or breaking the equivalence principle. Still, others have taken more radical routes. Some propose that space-time itself is an emergent phenomenon, that geometry and gravity arise from deeper quantum entanglement patterns. In such views, the event horizon may not be a fixed surface, but a kind of quantum phase boundary, where space-time behavior shifts from one regime to another. Yet, despite the variety of responses, the original AMPS argument remains a central problem in the field. It has not been definitively resolved. The tension it exposed between unitarity, entanglement, and general relativity continues to drive new research into the foundations of quantum gravity. Perhaps most intriguing is the idea that the paradox is pointing us toward a more fundamental understanding of space-time. In recent years, connections between quantum entanglement and space-time geometry have grown stronger. Work by Juan Maldacena and others has suggested that the fabric of space-time itself may be woven from entanglement. The slogan ER house EPR, which links Einstein-Rosen bridges, wormholes, with entangled particles, offers a glimpse into a potential unification of gravity and quantum theory. If true, this would mean that black holes are not merely astrophysical objects or gravitational anomalies. They are crucibles of quantum geometry, places where the most basic elements of reality are forged and tested. And the firewall paradox may be a hint that our current frameworks are incomplete. that the smooth, continuous spacetime of general relativity must give way to a richer, more nuanced quantum structure, one where boundaries like the event horizon are not just surfaces in space, but transitions in the quantum informational fabric of the universe. So where does this leave our falling observer? If firewalls exist, then your journey into the black hole ends not at the singularity, but at the horizon itself. You are annihilated the instant you cross, consumed by quantum energy too intense to survive. If firewalls do not exist, then your descent continues peacefully, as general relativity predicts, until the singularity finally overtakes you. The truth may depend on a theory we have not yet discovered, a complete theory of quantum gravity, one that unites the insights of Einstein with those of quantum field theory, might finally resolve the conflict. It might reveal that both perspectives are correct in different ways, or that neither tells the whole story. For now, the firewall paradox stands as one of the sharpest tests of our understanding. It is a crossroads between the known and the unknown, between the classical and the quantum, between survival and destruction. And as we step beyond it, we move into a realm of possibilities that stretch the imagination even further. Could black holes lead somewhere else? Could they connect to other regions of space-time? Could something lie beyond the singularity? A mirror, a reversal, a rebirth? To consider such questions, we must turn to a new class of ideas: wormholes, white holes, and the radical possibility that black holes might not be ends, but bridges. If the singularity marks the end of the road in general relativity, and if the firewall paradox hints at a deeper quantum foundation for space-time, then one cannot help but ask a bold question. Could there be something after a black hole? Could these extreme objects serve not only as gravitational traps, but also as portals, bridges, or rebirths? To explore this idea is to enter the domain of some of the most speculative, yet mathematically intriguing concepts in physics: wormholes, white holes, and the potential for space-time to reconnect in unforeseen ways. This story begins with Einstein himself. In the year 1935, Albert Einstein, along with fellow physicist Nathan Rosen, explored a solution to the equations of general relativity that described a bridge between two distant regions of space-time. Their work was not originally intended to describe black holes, but rather to eliminate singularities from the equations. The result, however, became known as an Einstein-Rosen bridge, a structure more commonly referred to today as a wormhole. A wormhole is, in essence, a tunnel through space-time. Imagine two distant points in the universe, perhaps two galaxies separated by millions of light-years. A wormhole would create a shortcut between them, a path through a higher dimensional geometry that bypasses the intervening space. In the analogy of a two-dimensional sheet of paper, if you fold the paper so that 2 points touch, then poke a hole through it, you've made a wormhole. In this visual metaphor, the wormhole connects what would otherwise be vastly separated locations. The Einstein-Rosen bridge solution was fascinating, but it had limitations. It was unstable. Any matter or signal attempting to pass through the bridge would cause it to collapse before completing the journey. Moreover, in the original formulation, the wormhole was non-traversable, useful as a conceptual device, but not as a passageway. Later developments in theoretical physics reopened the question. In the 1980s, Kip Thorne, Michael Morris, and Ulvi Yurtseva examined whether traversable wormholes could exist, provided the right conditions. Their work, which became widely known after being referenced in science fiction literature and film, proposed that exotic forms of matter, specifically negative energy, might hold a wormhole open, preventing its collapse. Negative energy is not science fiction. It arises naturally in quantum field theory, notably in phenomena like the Casimir effect, where quantum fluctuations produce a measurable force between closely spaced metal plates. If such energy could be harnessed, it might, in theory, be used to stabilize a wormhole. But even this possibility is shrouded in uncertainty. Creating, sustaining, and navigating a wormhole would require levels of control over matter and energy far beyond anything currently imaginable. Still, the mathematics allows it, and once the door is opened to such structures, more radical ideas emerge. One of them is the white hole, a hypothetical counterpart to the black hole. If a black hole is a region of space-time where nothing can escape, A white hole is a region where nothing can enter. In theory, it is the time reverse of a black hole, a structure that expels matter and radiation, but into which nothing can be absorbed. From the outside, a white hole would appear to erupt spontaneously, flinging matter outward. It would have an event horizon, just like a black hole, but one that works in reverse. White holes are solutions to the equations of general relativity, just like black holes. But no natural white hole has ever been observed. They remain entirely theoretical. Still, some researchers speculate that black holes and white holes could be connected, perhaps forming the two mouths of a wormhole. In such a model, matter falling into a black hole might emerge elsewhere in the universe, or even in a different universe altogether, through a white hole. This vision is highly speculative and faces many challenges. The interior structure of a black hole, as currently understood, does not allow for signals or particles to escape once they have passed the event horizon. To make such a model work, one would likely need a full theory of quantum gravity, a framework that smooths out the singularity, allows for causality to be preserved, and creates continuity between falling in and emerging out. Some ideas in loop quantum gravity offer a hint of this possibility. In these models, space-time is quantized, and the classical singularity is replaced by a quantum bounce. The collapsing matter reaches a minimum size and then expands again, potentially forming a white hole-like structure. If true, this would suggest that black holes are not ends but transitions, that every collapse leads to a new expansion, and that information is not lost but transformed. Other proposals suggest that black holes might eventually tunnel into white holes as they evaporate via Hawking radiation. Instead of disappearing entirely, the black hole would release its remaining contents in a final outburst, emerging as a white hole with no singularity. This process would preserve information, honor the unitarity of quantum mechanics, and avoid the paradoxes discussed earlier. Of course, these ideas remain untested. We have no observational evidence for white holes, wormholes, or quantum bounces, and the engineering required to detect or construct such phenomena is beyond current capability. But from a theoretical standpoint, they are not forbidden. They emerge from the same equations that have successfully described planetary motion, gravitational waves, and the bending of light. Even the concept of baby universes arises in this context. Some models propose that a collapsing black hole might spawn a new, self-contained region of spacetime, a pocket universe with its own expanding geometry, disconnected from our own. From our perspective, all we see is the black hole. From the perspective inside the baby universe, the black hole could be its Big Bang. This idea suggests that our universe might itself be the interior of a black hole in a parent universe, nested in a cosmic hierarchy. Whether or not these speculative ideas are realized in nature, they serve a deeper purpose. They show that black holes are not just endpoints. They are testing grounds for the very principles of reality. They challenge our assumptions about time, causality, and connection. They suggest that space and time are not fixed but emergent, shaped by deeper laws we are only beginning to glimpse. In recent years, renewed interest in wormholes has arisen from developments in quantum information theory. The idea that entanglement could give rise to spacetime structure, summarized in the bold proposal, ER equals EPR, connects Einstein-Rosen bridges with quantum entanglement. If entangled particles are connected by microscopic wormholes, then perhaps the fabric of spacetime itself is stitched together by networks of entanglement. This radical view suggests that geometry is not fundamental, but derivative, a consequence of information. If so, then black holes may be more than just astrophysical entities. They may be gateways to understanding the deep relationship between space, time, and information. They may reveal that the universe is not a passive arena, but an active, dynamic network built from entangled bits, stitched together by gravity and shaped by entropy. As we imagine falling through the interior of a black hole, perhaps into another region of space-time, we confront not just the limits of physics, but the limits of imagination. What lies beyond the horizon may not be destruction, but transformation, a bridge, a bounce, or a birth. And yet, whether these possibilities are real or merely mathematical, they all raise one persistent question. What happens to the information? If you fall into a black hole and the black hole evaporates and perhaps tunnels or transforms, where does your story go? As we move from the strange possibility of wormholes and white holes back to the question of what actually happens to anything that falls into a black hole, we find ourselves standing before one of the most profound and unresolved paradoxes in all of theoretical physics, the black hole information problem. At its core, this problem is not about what we see or what we feel as we fall into a black hole. It is not about spaghettification, event horizons, or singularities alone. Rather, it is about whether the universe preserves information, the details of what has fallen into the black hole, and whether that information is destroyed or somehow retained, even after the black hole evaporates. To understand why this matters so much, we must first understand how information is treated in physics. In classical physics, information about a system is conserved. If you know the positions and velocities of every particle at one time, you can, at least in principle, calculate their past and future with perfect accuracy. This determinism carries over into quantum physics, though with a twist. Instead of absolute certainty, quantum systems evolve probabilistically, but still in a way that preserves the total information of the system. This is known as unitarity. In quantum mechanics, unitarity means that if you begin with a pure quantum state, one with complete information about a system, that state evolves over time into another pure state. No information is lost in the process. Even though outcomes may be probabilistic, the wave function evolves in a reversible and predictable way. This principle lies at the very heart of quantum theory. Now, let us place this principle beside the concept of a black hole. If an object falls into a black hole, a book, a computer, a planet, a person, the classical expectation is that the object is gone. Its matter and structure collapsed into the singularity. From the outside, all that remains is the black hole's mass, charge, and spin. This is the essence of the no-hair theorem, which states that black holes are characterized by only a few simple parameters. All other details are wiped away. Then, if the black hole evaporates via Hawking radiation, the radiation emitted appears thermal and random, without any imprint of the original object's complexity. And here lies the paradox. If the object's information is truly lost, then quantum theory is violated. But if the information is somehow preserved, then how and where is it stored and transmitted? Stephen Hawking himself initially argued that the information is lost. His early calculations showed that Hawking radiation was featureless and contained no hidden structure to encode the details of what fell in. This position sparked decades of debate, because it implied that black holes were places where the laws of quantum physics broke down. It was a bold and deeply unsettling conclusion. Many physicists refused to accept it. The idea that information could be destroyed was considered worse than a mystery. It was a threat to the consistency of the entire theoretical framework that governs particles, atoms, and the structure of the cosmos. If information could be lost in black holes, perhaps it could be lost elsewhere too, and then physics would no longer be predictive. Over time, a variety of proposals emerged to resolve the problem. One of the earliest was black hole complementarity, proposed by Leonard Susskind and others. This idea attempted to preserve both general relativity and quantum mechanics by suggesting that no single observer can witness both the information falling in and the information being radiated out. From the perspective of the outside observer, information is encoded on the event horizon and gradually released via Hawking radiation. From the perspective of the infalling observer, the journey continues smoothly to the singularity. But since no observer can experience both realities, the contradiction is only apparent. Another idea, already mentioned, is the holographic principle, first proposed by Gerard 't Hooft and later extended by Leonard Susskind. This principle suggests that all the information contained within a volume of space can be described by data encoded on its boundary. In the context of a black hole, that means everything falling into the black hole is somehow recorded on the event horizon itself. This idea gained strong mathematical support from string theory and was spectacularly embodied in the ADS-CFT correspondence developed by Juan Maldacena in the late 1990s. According to this duality, a gravity-based theory in a higher dimensional space, like a black hole in a curved anti-de Sitter space, can be equivalent to a quantum field theory without gravity on the boundary of that space. In this holographic model, unitarity is preserved. Information is never truly lost. It is merely hidden in an unfamiliar, scrambled format, accessible through the boundary. In recent years, advances in quantum information theory have brought new tools to bear on the problem. Physicists have begun calculating what is known as the Page curve, a graph that shows how the entropy of Hawking radiation changes over time. According to quantum theory, the entropy of radiation should initially rise as the black hole emits thermal particles, then eventually fall as the information is released and the black hole shrinks. Hawking's original calculations showed a different result, a steady increase in entropy, implying permanent loss of information. However, newer work, particularly from researchers studying quantum extremal surfaces and entanglement entropy in holographic models, has begun to reproduce the expected Page curve. This suggests that, even in semi-classical models, the information might not be lost, but is encoded non-locally, in correlations spread throughout the radiation. These results hint that a full quantum gravitational theory will ultimately preserve unitarity, even during black hole evaporation. Stephen Hawking himself revised his position in the early 2000s, acknowledging that information might be preserved after all. He proposed that the radiation contains subtle quantum correlations that encode the information, though he did not provide a complete framework for how this worked. The shift marked a significant moment in the debate, though it did not end it. Still, the question remains, how does the information get out? Is it carried by Hawking radiation from the beginning? Does it leak out only near the end of the evaporation process? Is it released all at once in the final burst? Or is there a hidden layer of quantum gravity that reconfigures the entire process? Some theorists propose that remnants, tiny, stable objects left behind after evaporation, might store the remaining information. Others suggest that baby universes might branch off from the black hole, carrying the information into a separate domain. These ideas remain speculative and face significant theoretical challenges, including concerns about causality, stability, and energy conservation. And so the paradox continues to evolve. What is clear is that black holes are no longer seen as simple gravitational sinks. They are now at the center of our effort to understand how space, time, and information interact at the most fundamental level. They test our deepest assumptions. They expose the fault lines between theories that otherwise work beautifully on their own. The black hole information problem is not just a curiosity about what happens to falling matter. It is a gateway to understanding the universe's most basic fabric, whether resolved through holography, entanglement, quantum geometry, or some entirely new framework. It forces physicists to rethink the nature of memory, identity, and continuity in physical law. From the perspective of someone falling into a black hole, it may seem that the information is lost forever. From the universe's point of view, it may be preserved in patterns too subtle to see. And from the vantage point of future physics, the very distinction between inside and outside, between loss and recovery, may dissolve into a unified description we have not yet imagined. As we near the end of our journey, both conceptual and gravitational, we are left with a remarkable realization. Falling into a black hole is not just a physical event. It is a journey through the deepest questions of existence. But before we conclude, let us pause and reflect. What have we really learned by imagining this descent? What does falling into a black hole reveal, not only about the universe, but about ourselves and the limits of our understanding? After exploring the extremes of space and time, wrestling with paradoxes of information, and contemplating the possibility of new physics, we now emerge, not from the black hole, for no such return exists, but into a different kind of clarity. The journey inward has become a lens for seeing outward. In falling into a black hole, we are not only encountering the edge of physical law, but also the edge of human knowledge. And in that sense, a black hole becomes more than a gravitational object. It becomes a mirror to the universe, and a mirror to ourselves. From the earliest conceptions of gravity in Newton's time to Einstein's revolution in the early 20th century, humanity has sought to describe the cosmos with increasing precision. But black holes resist easy description. They absorb what we send in and return only silence. They leave us with equations that generate infinities, symmetries that collapse, and laws that seem to contradict each other when pushed too far. And yet, the attempt to understand them has revealed more about the universe than perhaps any other single class of object. Black holes have transformed how we think about space, time, entropy, information, and even causality. They have forced physicists to reconsider the meaning of physical laws at their most fundamental level. They have shown us that horizons are not just physical boundaries, but conceptual ones. And they have demonstrated that looking into the darkness often yields more insight than staring at the light. But these insights did not arise in isolation. They came through decades of observation, theory, failure, and rediscovery. They came through the work of minds across continents and generations: Einstein and Schwarzschild, Penrose and Hawking, Wheeler and Thorne, Maldacena and Susskind. Each added a piece to the puzzle. Each asked new questions that reframed what had previously been assumed. Observationally, black holes are no longer abstract. We have seen stars whirl around invisible centers in the cores of galaxies, their motions revealing the presence of supermassive black holes. We have observed X-ray emissions from matter spiraling into compact, unseen objects, and we have detected gravitational waves, ripples in the fabric of space-time itself, from the collisions of massive black holes far across the cosmos. In 2019, the Event Horizon Telescope gave us the first image of a black hole's shadow in the galaxy Messier 87. This image was not a photograph in the conventional sense, but a synthetic construction built from data collected by radio telescopes around the globe, using a technique called very long baseline interferometry. What it revealed was not the black hole itself, but the silhouette left behind as its gravity bent and trapped light. It confirmed predictions made decades earlier. It made the invisible visible. These achievements remind us that even the most abstract theories can be grounded in real phenomena. Black holes are not merely thought experiments. They are out there, billions of them, shaping galaxies, merging in darkness, whispering across space with waves of gravity. And they are still teaching us. Today, physicists continue to use black holes as testbeds for new ideas in quantum gravity, thermodynamics, and holography. Simulations explore how matter and light behave near their horizons. Mathematical models attempt to reconcile their properties with those of quantum fields. Space-based observatories are being designed to study them with even greater precision. But the most enduring impact of black holes may not be scientific alone. It may also be philosophical. Falling into a black hole challenges everything we intuitively believe about experience. Time slows and then breaks. Directions collapse. Vision distorts. Identity unravels. Laws that govern the stars and planets cease to apply. In a very real sense, the black hole is a metaphor for the limits of knowledge. And yet, we persist in asking what lies inside. We imagine the journey. We do not look away. That impulse, to press on, even when the answers are obscured, is what has always driven science forward. Black holes are not only endpoints, they are beginnings. The moment they were taken seriously as physical entities, the questions surrounding them began to reshape our theories of nature. From the entropy of horizons to the fate of information, from the holographic principle to the unification of forces, black holes have touched every major thread in theoretical physics. They are not isolated anomalies. They are the keystones of modern understanding. They also remind us of scale. The black hole at the center of our galaxy, Sagittarius A star, weighs several million times more than our Sun. It is vast beyond imagination, yet it fits within a region smaller than the orbit of Mercury. And then there are the supermassive giants, tens of billions of solar masses, at the centers of other galaxies, shaping the evolution of cosmic structure. They grow through accretion and mergers, influencing star formation and the flow of interstellar gas. At the opposite end are the tiny, theoretical primordial black holes, perhaps as small as mountains, formed in the earliest instance after the Big Bang. If they exist, they might still drift through the universe, cold and ancient, remnants of a time before stars and galaxies. In all their forms, black holes stretch the imagination. They unify the very large and the very small. They hint at symmetries yet undiscovered and connections yet unraveled. And in contemplating the experience of falling into one, step by step, moment by moment, we have retraced the arc of modern physics. We have passed through the geometry of space-time, the behavior of light, the mechanics of collapse, the riddles of quantum theory, and the paradoxes of information. We have stood on the edge of the known and peered into the unknown. So what would you see if you fell into a black hole? You would see light bend and time stretch. You would see the universe accelerate and then fade. You might witness the far future in seconds and then lose sight of the sky altogether. You would feel nothing as you crossed the horizon, and everything as you neared the center. Your vision would twist, your body would stretch, your understanding would shatter, and yet through this imagined fall, we have risen to new insights, new questions, and a deeper appreciation for the universe we inhabit. In that sense, the black hole is not just a destination, it is a journey into the heart of physics, into the architecture of reality, and into the power of the human mind to imagine, to reason, and to wonder. And as we look up into the night sky and contemplate the dark voids between the stars, perhaps we can now see them not just as absences, but as invitations, not as endings, but as mirrors. Because in seeking to understand what lies within the black hole, we come closer to understanding the universe itself. And in doing so, we come closer to understanding ourselves.